So, in this module we are going to look at fluid statics. So, fluid statics refers to those problems or that branch of fluid mechanics in which the fluid is not under motion, and it has a number of applications. So, let us look at the content first. We will be talking about pressure and then pressure distribution in a static fluid. We all of us know that P is equal to rho g h in a static fluid. So, we will derive this relationship and look at different applications of this. Then we will also look at in the subsequent lectures how we can calculate the hydrostatic force on submerged surfaces. These surfaces might be planar or these might be curved. Then we will look at how we can derive, using the principle of fluid statics, how we can derive the principle of Archimedes or Archimedes principle, which gives rise to the concept of buoyancy. Then we will look at fluid-fluid interfaces, capillarity effect, surface tension between two fluids, and when there are 3-point contact, solid, gas, liquid, or solid, liquid, liquid, immiscible liquid on a solid surface, then the concept of contact angle and wettability. So, in today's lecture we will look at pressure and pressure distribution in a static fluid. Now, as the term suggests that the fluid statics, so statics refers to that branch of mechanics in general where the body is not in motion. So, when we are talking about fluids, fluid statics will refer to that branch of fluid mechanics in which there is no motion of fluid is involved. Now, as we know that fluid can be gases or liquids. Gases in general, they are compressible in nature. So, we can have compressible fluids or incompressible fluids. Now, when it is incompressible fluids, then the fluid statics is also known as hydrostatics. Statics, as I said, it refers to no motion. So, that has an implication that when there is no motion, the velocity is 0 and the momentum, which is product of mass into velocity, is also 0. So, there is no momentum change involved, and by the definition of fluid itself, that a fluid deforms continuously under the application of a shear stress or shear force. So, if the fluid is not in motion, that means the fluid is not deforming, then there is no shear stress. So, the only stress that will be present and viscous forces which causes shear stress. So, viscous forces in a stationary fluid will be 0. So, we can say that in a stationary fluid, viscous stresses, as we know for a Newtonian fluid from Newton's law of motion, that viscous stress is proportional to shear rate, and when the shear rate is 0, viscous stresses are also not present. So, the only surface force present in a static fluid is pressure force. So, there are number of applications where these principles of static fluid static are needed to be applied. The first one that I have listed here is pressure distribution in above the earth surface and below earth surface. As we know that P is proportional to rho g h, where h is the height or it may be depth. So, when we go up in the atmosphere, the height increases. When we go down in the ocean, the height decreases or the depth increases. So, in both cases the pressure is going to vary, and any device or any person or any animal who is going in the atmosphere well above Earth's surface or deep in the ocean, the pressure at the depth or pressure at an elevation needs to be calculated. Okay. Then all the storage vessels or dams, tank walls, they have flat or curved surfaces. So, each of these will experience a force because of the hydrostatic pressure. So, we need to also know how to calculate this force on flat and curved surfaces. So, we will look into this problem. Then we all know the principle of buoyancy, Archimedes principle, that when a body is submerged in a liquid, then a force acts on it opposite to gravity. If the body is lighter than the liquid or the density of the body is lighter than that of liquid, then a net force will act opposite to gravity. But in any case, there will be a force acting on a body which is buoyancy force, and that will be equal to the weight of the fluid displaced by the body. So, that is what Archimedes principle is. We will look into it. And then in hydraulics there are number of applications. So, for example, hydraulic actuation and design of pressure measurement instruments. It can be simple manometer or mechanical pressure measurement instrument or electronic pressure measurement instruments. So, we will look at some examples of manometers. Okay. So, before we go into further details, let us look at or let us remind ourselves what is pressure. So, when we read thermodynamics or when we study thermodynamics, we talk about kinetic theory of gases, and there the thermodynamic property of fluid pressure comes into picture. So, it is defined as force per unit area. Now, what is this force? The force is caused by fluid molecules bombarding the surface. So, when you have a surface, you can have a real surface or an imaginary surface inside a fluid, then because of the molecular motion, all the fluid molecules will collide with the surface, and the net force that acts on this surface is what we call this force when we define pressure as force per unit area. So, of course, the net force will be normal to the surface. So, that is why the pressure force always acts normal to the surface, okay, on which it acts, and it is a compressive force. So, it is acting on the surface, not away from the surface. Okay. So, you have a let us say a vessel, and in this vessel if there is gas filled into it and there is a surface. So, the molecules in this vessel will be distributed randomly, and these molecules will have their random motion, and during this motion they will collide with the surface and cause a net force normal to this surface. So, this force per unit area is what is called pressure force. Now, this surface that we talk about, it may be a real surface or an imaginary surface. So, pressure, we can say that pressure can be at any point in the fluid, it is not only at the surface, but it is defined with respect to a surface. Now, pressure is a scalar quantity in itself. When we talk about the direction, it is the pressure force that acts on a surface. Now, the direction of this pressure force is determined by the surface on which it acts. So, when we are defining pressure, we need to have a surface also on which it acts. Now, it always acts normal and it will be compressive in nature. So, it will be acting on the surface, not pulling or not away from the surface. Okay. So, this will be the direction, whereas it can never have the direction this. So, this is not correct, whereas this is correct. Now, pressure on this surface, if we say pressure on the left hand side on from left to right, whereas pressure on the from the molecules on the right side will be acting from right to left on this surface. Okay. So, another property of pressure is that it is isotropic. That means that if you take any point in a fluid, if we again draw the same image and take a point in a fluid, then you can have a number of surfaces that pass from this point. So, on each surface the pressure will act normal to this surface. In order that this fluid molecule is static, there is no pressure difference in any particular direction. So, the force at this point or the pressure at this point has to be same across all directions. So, that means pressure is isotropic. So, pressure in all the directions will be same at a particular point in a fluid. Okay. So, the term isotropic means that any property that is same in all directions, then we call it this property to be isotropic. So, pressure is isotropic. It of course has a single value at any point in a fluid, and this principle is also known as Pascal's law or Pascal's principle. Now, we know that pressure is force per unit area. So, it can have different units. If you talk about kg force, so kilogram force per meter square or Newton per meter squared. It may have units of Pascal, bar or pound per square inch and so on. Now, because pressure when it is measured with respect to a reference pressure. In most of the cases when we are doing things in on the earth's surface, then it is measured with respect to the atmospheric pressure. So, it is often reported in respect to or with respect to atmospheric pressure. So, if the pressure is above atmospheric pressure, then we represent it as a gauge pressure. So, P gauge is equal to absolute pressure or thermodynamic pressure, what we call, minus atmospheric pressure is called gauge pressure. So, this term gauge pressure is generally used when we have pressure above atmospheric pressure. If pressure at a point or in a vessel or in a reactor is less than atmospheric, then it is known as vacuum pressure, or if we talk in terms of gauge pressure, then pressure will be negative. So, we say that 10 mm Hg vacuum, that means the pressure is 10 mm less than that of atmospheric pressure. So, this we need to remember that whenever any pressure is being reported in an experiment or in any problem, then we need to know or we need to ask ourselves, is this the absolute pressure, is this the gauge pressure, or is it vacuum pressure. So, now we will look at the relationship that we have known for quite some time, that P is equal to rho g h, where h is depth in the fluid. So, we know that the pressure is proportional to h, where h is depth. So, P is equal to rho g h, it increases with depth. So, let us derive this expression for pressure distribution in a fluid. So, we will consider a fluid element which is of cuboid shape. It has dimensions dx, dy and dz. We have a Cartesian coordinate system x, y and z, and the length of this cuboid fluid element along the x direction is dx, along the y direction is dy, and along the z direction is dz. So, we will apply Newton's second law of motion on this fluid element, which we already know that force applied on a fluid element on a body is equal to rate of change of its momentum. So, F is equal to d by dt of mv, and if we say that mass is independent of time, mass is constant, then you can write it F is equal to m dv by dt, or more commonly we know that F is equal to m a, where a is acceleration. Now, because the fluid is not moving, so this term is going to be 0. So, m dB by dt will be 0. So, we have that for a stationary fluid, the net force on the fluid will be 0. So, the only thing we need to obtain is what is the net force on this fluid element. Now, we talked about earlier that on a fluid element, we will consider two kind of forces, body force and surface force. So, in general in fluid mechanics problems, when we talk about body force, it will be gravity force, and when we talk about surface force, they are pressure and viscous forces. As we said earlier that in a static fluid, the viscous force is 0 because there is no motion. So, the only surface force we will have is pressure force, and then only body force that we will have is gravity. So, we need to calculate what is the body force, and we need to estimate what is the surface force on this fluid element. This fluid element has 6 surfaces. So, we will need to obtain the force on each surface and then sum it up together. Okay. Now, body force, as I said, it is caused by gravity. So, we will consider that body force is equal to if the mass of the fluid element is dm. So, body force will be dm into gravity, and dm is mass is equal to density into volume. So, if fluid element volume is dV, then we can write dm is equal to rho dV into g. Now, we can see that for this cuboid, dV is equal to dx, dy, dz. So, multiplication of the 3 sides will give us the volume of this fluid element. So, this is equal to rho dx, dy, dz. So, this is the body force. Now, we need to calculate the surface force on this. So, on this when we talk about surface forces, as I said that the viscous stresses are going to be 0 for a stationary fluid. Now, we need to find pressure force on each face. So, let us assume that the pressure at the point at the center of this fluid element, which we call point O, is P, small p. Now, we need to obtain pressure force on different surfaces of this body. So, we need to consider or we need to obtain the pressure on all 6 faces of the body, multiply it by the area or area vector. So, we will get the force on 6 surfaces and then we sum it up together. So, then we will get the total surface force that is being exerted on this fluid element. So, at a distance dy by 2. So, if we consider the surface on its right, then this surface is at a distance dy by 2 from point O. So, we can obtain pressure at this point using Taylor series. So, let us remind ourselves what is Taylor series, that using Taylor series we can obtain f x, knowing f at x is equal to a, we can obtain f a point at a point x, which f x is equal to f a plus f dash a. F dash a is derivative of f with respect to x. So, f dash is del f over del x. So, f dash a into x minus a plus double derivative of f with respect to x at point a divided by factorial 2 into x minus a squared and so on. So, because we are taking a elemental volume, so dy is small. So, that means dy squared will be small. So, we will neglect the higher order terms, second and higher order terms. So, if we apply Taylor series expansion, then we will obtain the pressure on the right surface as I have shown in the figure. So, pressure on the right surface will be P plus del P over del y into dy by 2. Now, somebody might say that why are we not considering the variations of pressure at the top and bottom up above y along the x direction and the z direction. So, if we are considering a linear variation of pressure, then we will see because when we are considering only the first order term, then we will see that even if we consider the variation of pressure on this surface in the x direction or in the z direction, then the terms will cancel out. So, on this surface we will consider pressure P right is equal to P plus del P over del y, which is pressure gradient along the y direction, into this distance dy by 2. So, distance from point O to the surface on the right, that is dy by 2, because O is at the center of this cuboid. Similarly, we can obtain pressure on the left face. So, the left face will be this face. So, this face will be again at a distance of dy by 2, but it will be minus dy by 2 because it is in the negative y direction. So, pressure on the left face will be P minus del P over del y dy by 2. So, now we know what is the pressure on the two surfaces, on the surface on the right and surface on the left, and by looking at it we can find out that when we talk about pressure along the y direction or the pressure force along the y direction, then the contribution will come for the surface forces from the left and right forces, because that is where the normal will be along the y direction. So, let us look at pressure force along the y direction. We multiply this force. So, if we look at the surface on the right, the pressure here is P plus del P over del y dy by 2, and the area of this surface will be dz into dx. So, the area is dx dz, and it is the area vector will be always outward normal on this surface. So, when area vector is outward normal, then we will have a force on this will be the pressure multiplied by area, and the direction of force will be negative. So, the area is outward normal, but the pressure will act in the negative direction. So, if ever we write pressure in terms of P into dA area vector, we will need to write dF is equal to minus P dA. So, if we write dF on a surface, it will be minus P d area vector. So, the area is positive. So, this is positive j direction or the unit vector j, but the force that will act on this surface will be in the negative direction. So, we can see here that the pressure multiplied by area dx dj into j and negative sign. Similarly, on the left surface, the pressure force will act in the positive y direction, whereas the area will be outward normal. So, the area vector will be pointing in the negative y direction. So, you can either just directly look at consideration of the force direction, or you can use this formula dF is equal to minus P dA, where area is a vector. So, when you use this, the pressure on the left face is P minus del P y del y into dy by 2, and the area is again dx by dz magnitude, and it will be minus j when you multiply it with by minus. So, then you get finally plus. So, when you sum these terms, you see that the term containing P, that will cancel out, and the net force or net surface force in the y direction is minus del P by del y dx dy dz. So, you see that dx dy z is the volume of this fluid element. If we do the same exercise for the surfaces which are say along the x direction. So, if we take this surface and the surface at the back, and when we sum up the terms, then we will get pressure force along the x direction will be minus del P by del x dx dy dz. So, you see the only difference from df P y we have here is from y is replaced by x. Similarly, the third force will be in the z direction, or the third component of this force will be in the z direction. So, minus del P by del z dx dy dz. So, next let us look and put together all the terms. So, the net surface force, and because pressure force is the only surface force now. So, net surface force, when we combine all this together, dx dy dz is common in all this. So, we will have minus del P by del x I plus del P by del y j plus del P by del z k, where I, j and k are unit vectors along x, y and z directions. Now, so we have obtained the surface force. We can see here that this term in bracket is basically gradient of pressure. So, let us remind ourselves what is gradient operator. Gradient operator which is operated on any scalar quantity and you get a vector quantity. So, gradient is minus del by del x I plus del by del y j plus del by del z k. So, it is not we do not need minus here. So, gradient operator is simply del by del x I del by del y j plus del by del z k. So, there is no minus here, that is a typo. Now, pressure gradient when we apply. So, we will get del p is equal to del p by del x I plus del p by del y j plus del p by del z k. So, finally, we see that the surface force d f is minus del p dx dy dz, where this is dy dx dy dz is the volume of the fluid element. So, the surface force is negative of pressure gradient. So, we can see that in the calculation of surface force, it is not the pressure itself, but the pressure gradient which is important in a static fluid. So, now we can combine the body and surface forces and obtain total force on this fluid element. So, the total force we might recall from the previous slide that the total force is total body force is mg, which is rho, where rho is density into dv, dv is dx dy dz into g. So, this is the body force, and as we saw just above, the surface force is minus gradient of p dx dy dz. So, the total force, if we take dx dy dz out, will be minus del p plus rho g, or we can replace dx dy dz by the volume of this fluid element. Okay. So, now when we started deriving this, we said that we are going to apply Newton's second law, and because there is no motion, so the acceleration is 0. So, we simply have that the force on this, the net force on the fluid element is 0. So, we have minus del p plus rho g within bracket multiplied by the volume of the fluid element is equal to 0. This is volume. So, we cut by a horizontal line. So, we have minus del p plus rho g is equal to 0, where del p is net pressure force per unit volume, because we have divided by the volume. So, gradient of p is pressure force or the net surface force per unit volume, whereas rho g is the net body force per unit volume. So, the surface force and body forces, they will balance each other. So, we can write this equation, this is in the vector form, we can write in different component forms. If we write along the x direction, we will have minus del p over del x plus rho g x is equal to 0. Similarly, along the y direction, minus del p over del y plus rho g y is equal to 0, and along the z direction we will have minus del p over del z plus rho g z is equal to 0. Now, if we choose our coordinates such that if g acts in the negative z direction, then we will have this term to be 0 and this term to be 0. So, that means pressure will be constant along the x direction, pressure will be constant along the y direction, and we can write this is equal to, this term will give us, because the pressure will depend only on z. So, we can write this minus dP over dz minus we can write this is equal to k. So, where g is the value of gravitational acceleration. So, we can have dP by dz is equal to minus rho g. Okay. If we write in terms of depth, if h is depth, then we can write P is equal to rho g h. Okay. So, now we will look at an example for a manometer. So, manometers, we know that they are simple, inexpensive, or the cheap devices which can be used to measure pressure. So, a very simple device or a very simple manometer is what we call U-tube manometer. So, which has U shape, and let us say there is a flow in a pipe, and it can be used to measure pressure difference between 2 points 1 and 2. So, the manometer is filled with a fluid, and the difference of the height of fluid in the two arms of the manometer will give us the pressure difference between the 2 points. So, when applying a manometer principle, we need to remember that the 2 points at the same elevation in a continuous region of the same liquid are at the same pressure. So, if we let us say this is a fluid water, and then manometer can have a different fluid, let us say this is CCl4. The choice of fluid will depend on the magnitude of pressure and density of. So, depending on what is your estimated pressure difference or what order of pressure difference you are going to get, accordingly you will choose a fluid which is of the density, so that the height difference can be significant. So, the accuracy of the manometer is good, or the sensitivity of it is good. So, coming to this point, that 2 points at the same elevation in a continuous region of same liquid are at the same pressure. So, that means if we take 2 points at this region, then point say A and point B, they are in the same fluid. So, they will have same pressure. So, P A and P B will be same at this point. If we take another line, horizontal line, and say point C and point D, they will be at the same pressure. Okay. So, we need to remember this, and the other thing is that as we go deep in a fluid, then along the depth the pressure will increase. Okay. So, the pressure increases with increasing depth in a fluid. Okay. Now, we will look at an example. So, if we have a manometer where it is filled with 4 different fluids, and the fluid 1 is open to atmosphere. So, the pressure at this point we can say that atmospheric pressure. Okay. So, what we need to find out is pressure at point A, or the relationship between, or the difference between P A and P atmosphere. So, we can start with that pressure at point A will be equal to, so if we look at this point, let us call this point, we will name all the points. So, point B, point C, then point D, E, and we already have A. So, we can write that P we can write P C minus P B, where P B is P atmosphere, so that will be equal to rho 1 G H 1. So, P C, where the pressure will be higher than at point B, because it is at a greater depth in the same fluid. So, P C minus P B is equal to rho 1 G H 1. Now, we will find out the difference between pressure at point D and point C, which will be equal to, so we know that the pressure at point C here and at the same location in this fluid is same, because this is a continuous fluid region, and so at the same height the pressure will be same. So, we can write that P D minus P C is equal to minus rho 2 G H 2. The minus sign is because of the fact that D is at a height when compared with C. Okay. Now, we will find difference between point D and point E. So, we can write P at E minus P at D is equal to, again the point E is higher than point D. So, we know that the pressure in fluid 3 at the two elevations will be same. So, we can write P E minus P D is equal to minus rho 3 G H 3. Now, finally, we can write P A minus P E, that will give us A is at a depth than E. So, and the height difference between the two is H 4. So, the pressure at A will be higher, and we can write P A minus P E is equal to rho 4 G H 4. When we combine all this, then we will get P A is equal to P atmosphere. So, this will cancel out, P D will cancel out, P E will cancel out, and you will get P A minus P atmosphere of, if we take atmospheric pressure on the right hand side. So, we will get P A is equal to P atmosphere plus rho 1 G H 1 minus rho 2 G H 2 minus rho 3 G H 3 plus rho 4 G H 4. So, it becomes a straightforward if we remember the two principles, the first one being that the pressure at 2 points having same elevation in a continuous region of fluid will be same. The second is that the pressure increases in the same fluid, the pressure increases along the depth. Okay. So, that is all for this lecture.